All right, we've got a center of mass problem where I give you a shape and you have to find the center of mass. This problem has a continuation where you keep going and find the moment of inertia. So we have find the x-coordinate of the center of mass of the triangle shown in the figure. The mass of the triangle is not uniformly distributed. Rather, it has a density of sigma equals x over 6 kilograms per meter cubed. The total mass of the triangle is 1 kilogram. I had made a minor correction here where the units should be kilograms per meter cubed. Since this is a surface density, it should come out to kilograms per meter squared, which happens when we multiply by x. One of the meters cancels out. I set the total mass of the triangle to be 1 kilogram, but if you're a Calc 3 student, you could spot that that also is a mistake, and I'll leave that as an exercise to the reader to find what the real mass of the triangle is. Anyways, let's get started, and we want to write down the formula for the center of mass in the x direction, which is 1 over the total mass times the integral of x dm across the total shape. It's a mysterious type of integral. It's not one that we solve as is pretty much ever. Rather, we need to rethink this integral in terms of the Cartesian coordinates, x, y, or z. And so to do that, we need to think about this dm part and think about how we can get a dm in this situation. I specifically asked for the x coordinate because doing the y coordinate is just a little bit more challenging for us in this class. And I thought this was instructive anyways. So I'm going to start by drawing a little line representing a dx, or sorry, a dm, a little piece of mass. Now I've chosen this slice since sigma, our surface or our area mass density, is dependent on x. So x over 6 kilograms per meter cubed. And so this is going to allow us to put it into an integral pretty nicely. So if we have this piece of mass here, this is our dm, okay? And it's going to be equal to some sort of a density, in this case a two-dimensional density, the sigma, times an area element dA, a little piece of area. And we can already kind of see what that is with the shape of this being somewhat of a rectangle, a little slice, a little tiny slice, right? So small a slice that the width of this rectangle is dx. The height of the rectangle, well, whereas dx is kind of the same regardless of which piece you've chosen, this one or this one or this one, the height is variable, right? This height is dependent on this line. This height is y. But we've taken algebra 1, and so we can describe this line with a function. If we just look at the slope, the rise over run, we've gone up 2 units over 3 units, then we can describe this y as being 2 over 3x. We now have it described in terms of x. So our dm is going to be, well, sigma, we have a function. I gave you that function, x over 6 kilograms per meter cubed. I'll put little square brackets to remind you that these are units, and this is not, mass cubed, so meters cubed. The dA is, well, the area of a rectangle is base times height. Our rectangle has a height of y, which is 2/3 x, and a base of dx. And so this is our complete mass element dm. And this allows us to rewrite our integral xcm is equal to 1 over the mass, where we integrate, and I'll come back to the boundaries here, x dm. So dm is x over 6 kilograms per meter cubed. I'll keep the units attached. 2/3 x, and then our friendly dx to finish the integral. Now the boundaries here, since we're integrating across x and we want to integrate across the whole shape, then clearly we're going to integrate from here to here, from the beginning to the end, which is 0 to 3 meters. And so we have, if we start plugging things in now, and actually let's simplify this integral a bit. I see a lot of numbers, just constants multiplied next to each other. We can pull them out of the integral. And so this is xcm 1 over, well, the total mass I said was 1 kilogram. And what can we pull out of here? So we have, I see a 2/3, a 1 over 6, and the kilograms per meter cubed. So I'll pull all that out. 2/3 times 1 over 6 is 2 over 18, or 1/9. And we'll pull the units out too, kilograms per meter cubed. Go ahead and treat them as if they were just constants. Kilograms per meter cubed. Let me put this guy in brackets as well. Now what's left over is the integral from 0 to 3 meters of, well, x times x dx, x squared, sorry, not x squared, x cubed dx, cubed dx. And that's not a hard integral. That's the first kind of integral that you learn, a polynomial. And so over here on the left, well, I see actually these kilograms can cancel. That's pretty nice. On the left we have 1/9 with meters cubed on the denominator. And out of the integral, we have, well, integral of x cubed is we add 1 to the exponent and divide by that number. So that's x4 over 4, evaluated from 0 to 3 meters. And that's pretty lucky because we put in the 0 and that term will go away. And so all that's left is 1 over 9 meters cubed times 3 meters, put these in parentheses, all raised to the 4th power over 4. And notice we have meters, which are going to be raised to the 4th power, and we're dividing by meters cubed, so our answer is going to be in meters, which is what we're looking for because we're looking for x, the x-coordinate of the center of mass. 3 to the 4th is, well, 3 squared times 3 squared, or 9 times 9. One of those 9s will cancel, and we're left with 9 over 4 meters, and that's our answer for the x-coordinate of the center of mass. Hopefully that makes sense. This problem really hinges on this step right here, figuring out what is your dm. That is the key sort of difficult part of this problem. And again, the total mass actually is not 1 kilogram. I'll let a Calc 3 student figure out what the mass actually is of this shape. And we'll carry this forward, carry this, and even the dm, use it in the next part of the problem where you find the moment of inertia as it rotates about the y-axis. All right, good luck.